Okay, so with your triangle, please, I would like you to go ahead and I would like you to mark our 3 angles. Angle 1. I'd like you to mark angle 2. And I'd like you to mark angle 3. And then what I want you to do is I want you to tear the angles off of your triangle. And I want you to use these pieces and prove to me that the sum of the angles in a triangle is 180 degrees. Set, go. So here's what's kind of cool. I'm seeing lots of success. If you take your 3 angles that you marked and you put your markings together, you end up with a straight angle. You end up with an idea that all of those, sum of those angles together equal 180 degrees. We call that a physical proof. So you guys all had random triangles and they were all different sizes and shapes and whatnot. And you could take each of those angles and rip them off and talk about 180 degrees. Now we're going to talk about why. Maddie, you have a question? Yep. So a circle is going to be 360 degrees around. And that's what we named it, just arbitrarily. So we have that 180 degrees. All right, first I want to talk about your homework real fast. So that conversation comes back into play with what's at the end. But first of all, let's talk about what's at the top. Now, wow, what a mess I have. So take out your homework, please. And we'll talk about some quick answers, a cumulative review. Did you remember what each of these notions means? Well, that makes that nice and blurry. When the 2 letters are together, smushed together, that means the distance from E to H. So in the diagram of collinear points, we have those given equalities. So now I have the distance from E to G is 8, G to I 16, H I 12, E I 24. Find the coordinates of B if M is the midpoint of AB. So here's my work here for A. This endpoint, 7 plus some letter X. 7 plus some letter X divided by 2 is equal to 9. 5 plus some letter Y divided by 2 is equal to 7. I do the math and I get my midpoint of 11.9. For 6, negative 3 plus some X value divided by 2 is equal to 1. 5 plus some Y value divided by 2 is equal to 9. So I get the point 513. With your table group, will you please have a conversation about our inverse, converse, our P's and Q's? Go ahead, turn and talk. Go. mark that? Owen done? All of it? The back too? Pretty good. I'll buy it. All done? Yeah. All done?
Does it ever do it with this point?
That's fine. I don't really know how they got okay. So when we start talking about 13 through 16, a review of our angles. 11 and 12, when I went to solve those, I did my work down here, and I just gave my justifications. 11, x is equal to 20. 12, x is equal to 13. So let's talk about the proof real quick. I'm given the fact that these lines are perpendicular. And what I want to prove is that 1 plus 2, their measure is the same as w, y, x. So I say that they're perpendicular because that's what's given. And then I go ahead and I say that they are both right angles by the definition of perpendicular. And then I go ahead and I say that they are equal to 90 degrees by the definition of right angles. And then I go ahead and I say that 1 plus 2 is equal to angle XYZ, because the angle addition postulate. And then I have those two angles are equal to each other. And that's the transitive property, because they're both congruent, or they both have a measure equal to 90 degrees. And then I substitute 1 plus 2 in for XYZ, and then I get that by subpo. Any questions on that? All right, on the back, lots of, like, I didn't get this. Okay, say Eratosthenes. Eratosthenes is, okay, so over 2,000 years ago, Eratosthenes estimated the Earth's circumference by using the sun's parallel rays. On a day when the sun shone exactly down a vertical well in Sine at noon, he measured the angle the sun's rays made with a vertical stick in Alexandria that was 575 miles away. The measure of the angle of the stick in the sun's rays was about 7 degrees. So this is what we have as values. How did Eratosthenes use this fact to estimate the Earth's circumference? So I have a video. Let's see if it's going to load.
This is the checkers game where grandson
And I don't know if you'll be able to hear it.
This is the kitchen where the new boyfriend will unofficially become family. These are the Verbo vacation homes.
In the mid-20th century, we began launching satellites into space that would help us determine the exact circumference of the Earth, 40,030 kilometers. But over 2,000 years earlier in ancient Greece, a man arrived at nearly that exact same figure by putting a stick in the ground. That man was Eratosthenes, a Greek mathematician and the head of the Library of Alexandria. Eratosthenes had heard that in Syene, a city to the south of Alexandria, no vertical shadows were cast at noon on the summer solstice. The sun was directly overhead. He wondered if this were also true in Alexandria, so on June 21st he planted a stick vertically in the ground and waited to see if a shadow would be cast at noon. It turns out there was one, and it measured about 7 degrees. Now, if the sun's rays are coming in at the same angle at the same time of day, and a stick in Alexandria is casting a shadow while a stick in Syene is not, it must mean that the Earth's surface is curved. And Eratosthenes probably already knew that. The idea of a spherical Earth was floated by Pythagoras around 500 BC and validated by Aristotle a couple centuries later. If the Earth really was a sphere, Eratosthenes could use his observations to estimate the circumference of the entire planet. Since the difference in shadow length is 7 degrees between Alexandria and Syene, that means the two cities are 7 degrees apart on Earth's 360-degree surface. Eratosthenes hired a man to pace the distance between the two cities, and learned they were 5,000 stadia apart, which is about 800 kilometers. He could then use simple proportions to find the Earth's circumference. 7.2 degrees is 1/50th of 360 degrees, so 800 kilometers times 50 equals 40,000 kilometers. And just like that, a man 2,200 years ago found the circumference of the entire planet with just a stick and his brain.
Question, could you hear that in the back? Yeah? Okay, so would you please, with your table group, summarize how he did that? On your mark, set, go. Talk about it. Tell the story. Who thinks they can summarize for me? Summarize for me, please. Anybody? Tell me the story. There was this dude named Eratosthenes. And what did somebody tell him that made him curious? So they're thinking he kind of already knew that, but this validated that concept. Austin? Yeah, so somebody came and told him that in Syene, now I know how to pronounce that, in Syene, the sun is directly overhead at the summer solstice, and there's no shadow caused. He was like, oh, that's pretty cool. And then over in Alexandria, he wondered if that would be. So he stuck a stick in the ground. And you're like, no, wait, he was supposed to stand the stick straight up and down, but notice it was to him, right? But when the sun's rays came in at this parallel relationship, the stick created a 7-degree angle with the earth that he could tell. So when he measured that, he used alternating what? If these are parallel, and this conversation here is the transversal, do you see the alternating interior angles? So he's got a conversation here with my 7 degrees and here with my 7 degrees. So if it's 7 out of 360 degrees, that's his part to whole. So if this was a 7-degree relationship, don't you love the guy that he pays to go for a walk? Go for a walk and count. Have you ever tried to count something, lose track in the middle, and have to go back and start over again? He's like 578, and someone's like, hey, how you doing? He's like, ugh. So he paid a guy to walk all the way to count those steps. Now the video has it in metric. My data here is in standard miles. But it's interesting when he sees that this is the part and he gets to use a proportion to solve for the whole. Kind of cool. We like that story. It's definitely interesting. All right, here's this next piece that I want to talk about. Would you and your group mates please compare all of your answers and see if they match mine? On your mark, get set, go. Compare.
No, I almost threw it. You know how you can get 100 equal one stars? Yeah. You know you can get 100
All right, come back. There's a couple of these stories that I want to talk about specifically. You know that 1 and 5 are alternating interior angles, and by the way, we're given first that these two lines are parallel. So if you don't have those triangles drawn, please add them to your drawing, because none of this works without these parallel lines. All right, I'm given A and B are parallel. 1 and 5 are alternating interior. 1 and 4 are consecutive interior. 3 and 6 alternating interior. 3 and 7 consecutive interior. So we have all those relationships down. Here's where I want you to study the diagram. Look at the diagram and study. I want you thinking, what the heck is going on here? Because the measure of angle 1, 2, and 3 is 180 degrees. The sum of their angles together is 180 degrees. That's a straight angle. That's a straight line. But check out, I can substitute 5 in for 1, 3 in for 6, and you just have your second proof of the triangle sum theorem. Your first one was when you tore off your little angles. The second one is right now, because these two angles are congruent and these two angles are congruent. I know this plus this plus this is 180, so this plus this plus this is 180. Boom, you just proved the sum of the angles on a triangle is 180 degrees. That's one of our theorems we're going to be talking about today. The next one is pretty cool, because when I'm talking about the measure of angle 4, when I'm talking about describe the relationships between 4 and 2 and 6, you know that 4 and 5 are supplementary, so they add up to 180 degrees. And you know 5 plus these two equal 180 degrees. So if these 2 plus 5 is 180, and this plus this is 180, that means that 4 has to be equal to 2 plus 6. Do you see it? With your group mates, tell me how you know that 7 is equal to 5 plus 2. Go. I should hear you talking. Can anybody explain it to me? What is the relationship between angle 7 and 2 plus 5? Go ahead, Kim. Okay. So, 7 and 2 plus 5, not 2 plus 1. But that's pretty interesting because 7 is alternating interior angles with 2 plus 1. 1 and 5 are the same. 7 is congruent to 2 plus 1. 7 is congruent to 2 plus 5. I'll buy that, Kaden. That's good thinking. Okay, homework away. That was a nice little preview. And take out today's note sheet, 4-1. A polygon is a closed figure with sides. So by definition, a polygon is our most basic description of what we're doing in two-dimensional figures. A polygon is a closed figure with sides. Here's some things that you need to know that they are not. A polygon does not have curves. A polygon does not have vertices with more than 2 segments coming at them. So do me a favor, take a look at these 5 shapes, circle which ones you think are polygons, and cross off the ones that are not polygons, and we're going to get very good at using the word because. So that's your justification, that's your proof. Circle the ones that are, cross off the ones that aren't, and mark that go. Do it. Tell me one to cross off. B. I'm crossing off B. Why? Because this one has a curve. Tell me another one to cross off. How come? It's not closed. And we can talk about the fact that it's open. Give me another one. Yeah. And A has to do with this story here because this vertice has 3 segments coming from it. So the vertex has greater than 2 segments. And that's the one that might end up messing you up down the road. Make sure you understand why those are not polygons. Okay. Our basic triangle. A triangle is going to be a polygon with 3 sides and 3 angles. So when we talk about a triangle, it has 3 sides and 3 angles. We name our triangles with a triangle symbol and the 3 letters of the vertices. And I don't care which order those vertices go in. You can call that triangle ABC. You can call it triangle BCA. You can calling it triangle CAB. You can call it triangle BAC, ACB, CBA. I think I got them all. Just as long as you use all 3 letters of those vertices. We're going to classify our triangles 2 ways. We're going to classify them by sides, and we're going to classify them by angles. You can be classified a bunch of different ways. We could classify you by what grade level you're in. We could classify you by what math class you're taking. When you're talking to your friends, you can be classified by what lunch you have. You could be classified by a number of different ways. Every triangle we are going to talk about by sides and angles. If a triangle is scalene, it has no congruent sides. Say the word scalene. If a triangle is isosceles, It has at least two congruent sides, and this is an important conversation because our equilateral triangles are a special kind of isosceles triangles. So equilaterals where I have three congruent sides. If I classify my triangles by angles, I can have an acute triangle where all three angles are smaller than 90 degrees. I can have a right triangle where it has one right angle. Or I can have an obtuse triangle where I have one angle is greater than 90 degrees. All right, so come back to your triangle. Build it back. See if you can put your angles back on your triangle. And I want to see if you have an acute, right, or obtuse triangle. And the easiest way to do that is every time I hand you a piece of paper, I gift you 4 right angles. I gift you 1, 2, 3, 4 right angles. And you can take this right angle, you can hold it up, and if it matches, then, oh, maybe I even want to see how this angle compares here. Oh, it's smaller than my right angle. So when I look here, I can compare each of my angles to what I know is right angles. And I have 3 angles that are smaller than, 3 angles that are smaller than my right angle. So I can say that I have an acute triangle. Talk to your group mates and ask them what kind of triangles they have. On your mark, set, go.
You have a right triangle.
Did you have one of the right ones? Yeah? Acute right or obtuse? Oh, you lost your third angle.
I lost my
Oh, there it is. Go on. Ariana lost hers too. Anyone have an obtuse? Anyone have an obtuse? Anyone have a right? Rest of us are all acute. It's fun. We can talk about acute little angles. The kids that struggle with this, they'll understand. And you need to talk about you can only ever have one right angle in a triangle. Only one obtuse angle in a triangle. But in order for it to be acute, you need 3. Think about why. I only have 180 degrees to begin with. If I allocate 90 of them to a right angle, I don't have enough for 2 more angle measurements. Does that make sense? Each triangle can only have one right angle at a time. All right. Our triangle sides are scalene, isosceles, or equilateral. And we need either measurements given to us or the ability to measure to make those determinations. So we won't worry about that yet. All right, some more vocabulary. If we're talking about an interior angle, we're talking about one of the 3 angles inside of the triangle. And like you figured out, the sum of the interior angles is always 180 degrees. And an exterior angle is going to be an angle that's supplementary to an interior angle. The sum of all the exterior angles is 360. We're going to talk about that more in a little bit. Our remote interior angles are going to be the 2 non-adjacent interior angles. Think of the other 2 angles. The angle is not a part of the linear pair. So if this is my exterior angle, my 2 remote interior angles are all the way on the other side. And that goes back to our warm-up when we talked about the relationship between 4 and 2 and 6 and 7 and 2 and 5. These two are the remote interior angles to 7. All right. What do these symbols mean? These ones. Anam. What do the symbols mean? What measurement? So these measurements are what tells us about congruence. So if I have one hash mark on each of these, that means that the distance from B to C is the same as the distance from C to D, is the same as the distance from D to B. If I had to classify this triangle by sides, I would call it an equilateral triangle. Therefore, that triangle is equilateral. If I come over here, I can go ahead and know that this triangle and this triangle has two congruent sides. So the distance from B to D is the same as the distance from B to A. So therefore, triangle ABD is isosceles. So just make sure that you understand what those hash marks mean, because that has a lot to do with information that we need regarding the lengths of the sides of our triangles. All right. Practice. Classify each of these triangles by angles and sides. Give them each 2 vocabulary words from the front. Are you mark, set, go. All right, let's talk about these. What I'm talking about, this first triangle, as soon as I see this, I know that by angle I have a right triangle. As soon as I see this, I know that I have 2 congruent sides. So it's isosceles. As soon as I see this, I know that my triangle is obtuse. And granted, I don't have any information about any congruent sides, so my conversation is going to assume that is a scalene triangle. All right, this next one, it is definitely a cute little angle because I see 3 less than 90-degree measures. But now I see that it is also equilateral. And I'm curious what this means. And that is because we have another term that I want to make sure you have write down, which is equiangular. So an equilateral triangle is also equiangular. So we want to go back here and we want to add that vocabulary term. It's equiangular when I have 3 congruent angles. It's a special kind of acute triangle. if I have all three are 60 degrees. All right. So now we have some sketches, and I heard the one group is already working on it. I want you to sketch each triangle, and I want you to find the 3 that are impossible on your mark it, set, sketch. All right, I'm going to go with 2 impossible. Does that sound better?
Yeah.
Let's argue. Ready? If I have 3 different lengths, and all of these angles are smaller than 90 degrees, I have an acute scalene. I'm okay with that, right? All right. If I have 2 congruent side lengths, and this is smaller than 90 degrees, I have an acute isosceles. Here I have an obtuse isosceles. I tried to make that 90 degrees. Did I do an okay job? Let me get a right angle and test it. Did I make it bigger? Ooh, just barely. Right? I could have made it wider. Okay. Make it open just a little wider. And I could have an obtuse isosceles. An acute equilateral, and I'm going to go ahead and use my new vocabulary word and call it angular. It's equiangular, so maybe this is the one that they were talking about. But all those degrees are less than 90 degrees. They're all 60, and all of those are the same. So I'm okay with that. I cannot have an obtuse angle that's equilateral because this obtuse angle takes up more than its 90 degrees, and that doesn't give me the same amount of degrees I can allocate to the other angles. Does that make sense to you? Okay, if I have a right scalene triangle, our most famous Pythagorean triangle is the 3, 4, 5. That's definitely scalene. A right isosceles is also possible. These angle measurements are going to be 45 degrees. And I cannot make a right equilateral because all equilateral triangles are 60 degrees. So that wouldn't be possible. So maybe these 3 that he's talking about might be the fact that this is equiangular, but I'm going to push back against that. All right, real quick before lunch, 2 triangle sum theorems. This one we've already proven. The sum of the measures of the interior angles of a triangle is 180 degrees. And we've already used parallel lines to show that 1 has the same degree measure. Angle 3 has the same degree measure. So when I'm adding them to angle 2, that's how I get a sum of 180 degrees and a sum of 180 degrees. So take the time to do whatever drawings are necessary for that to make sense to you. The corollary, of course, makes sense. If I have a 90-degree angle, then my 2 acute angles are going to have to be complementary. And we'll talk about what a corollary means. Because a corollary is just a, oh yeah, while we're at it. All right, off you go. Have a good lunch.